Enjoy while you got it. Enjoy while you got it. You know what? This is discrimination against Group C. Discrimination. Get good, Group C. What? Are you giving it to everyone? No! Looks like Group C not good. Is there a reason for it? This is being nice.
So here's the truth. 5 groups did really well, and 1 group did much better than before. So as an encouragement, everybody gets +2. But starting next week, since you're all good, we're going to look for superior. Keep it up, you guys. Okay, so I do have one other announcement. I must announce this as per university regulation. A student in this class tested positive for COVID and was exposed before Monday's lab and before Wednesday's lecture. So potentially we're all exposed. But if you're vaccinated, you don't have to worry. If you don't have symptoms, you don't do anything. If you're not vaccinated, you just have to go test. Okay. All right. Let's start another thrilling subject. And spectroscopy. So who likes the light physics of light? Who likes? We have 3 people only. Okay, then this would be, a lot of the information will be kind of something you already know, learned about, but we're going to learn about it in context of now. And spectroscopy really is going to be applied throughout the semester in different ways. You already had some of that in HPLC where we did the capital using UV absorption. So a lot of essays are based on absorption of light or fluorescence of light, or even refraction, like refractive index, and also light scattering. So a lot of light-matter interaction that helps us in identification and quantification. So we'll start from the very beginning and tell me what you know about the light wave. Okay, so the following are associated with the light wave: electric field, magnetic field, or photons of light. Many? Huh? Only C? Okay. Ellery, what were you going to say? Did you have your hands up? Oh, tricked me. Shri. A and B. Can you? A and C? Abi? Abi, when's the ticket? So all of the above. So in a light wave, you have electric field and magnetic field. And also, this is the wave-like characterization, but also there are pockets of energy in a wave of light. We call them photons of light. So we're going to talk about the light wave in different manner, but mostly when we talk about absorption and fluorescence, we really care about the photons of light that gets absorbed versus fluorescence. Following spectroscopy as means of analysis, detection can be based on Absorption of a photon, I kind of answered some of that. Absorption of a photon, emission of a photon, or dissipation of heat. Drew? All of the above, Drew says. Page? It's A and B. Okay, so A and B, because dissipation of heat is going to be a very, very small amount of energy that cannot be really measured and detected for quantification. So the dissipation of heat is very, very small. The heat that is produced is very, very small. So how is heat generated? Is usually when you go from ground state to excited state, and then you want to go back, some molecules or atoms go back by giving out a photon of light, some go back by dissipation of heat, and some go back to ground state by doing both, fluorescing and giving heat. But the fluorescence and the absorption are measurable. We can measure them. Dissipation of heat, because of being very small increments, really hard to measure. So it's not really used as means of analysis. It happens, but when the relaxation happens, but it's not used as means of detection or analysis. Okay, so the spectroscopy basically is a study that looks at interactions of a matter and light, electromagnetic radiation of light. So the interaction happens in so many different ways. But first, what's the matter? The matter can be different species. So either it's a molecule or it's an atom. So some of you did atomic absorption this week. The species in that case is in atom form. So during atomization, when the flame breaks down the molecule bond, you end up with atoms that absorb light. So that is applied in atomic absorption. Or you're looking at the absorption or fluorescence or general interaction with light of a molecule, not an atom. Now the interaction is either you absorb the light, you emit it back, the matter might diffract the light, or it might scatter the light. And there is another one here that I'm missing, which is refraction of the light. So we will talk mostly about absorption and fluorescence, but we're going to talk about light scattering, diffraction, and refraction of light a little bit. And what's important also in spectroscopy is the region where you have the light interacting with the matter. So the region is basically has to do with the characteristics of the wave, okay? And the characteristic of the wave is looked at as the wavelength. And based on the wavelength, you have different radiation categories. So the most categories here in color that are related to us in analysis is UV, visible range, and infrared range. So a lot of our application analysis is in this range. You don't have a lot of analysis, microwave and radio waves. These are not really used for quantification or identification. One other criteria that is important, and we will go over it quite a bit, is the wavelength. The smaller the wavelength, the higher the energy. The longer the wavelength, so the shorter, I would say, instead of smaller, the shorter the wavelength, the higher the energy, and the longer the wavelength, the lower it is. Hence the lighter red to stronger. Okay? So UV carries more energy than infrared, for example, and we will talk about that in more. This is kind of an overview. Okay, so in spectroscopy, really we have UV vis absorption, we have infrared absorption, we have fluorescence. These are all under spectroscopy. Atomic absorption, it's its own category because we're looking at specifically atoms and identification and quantification of elements. Inductively coupled plasma emission. It also has to do with atoms, but here we measure absorption, here we measure emission. I think on Monday, potentially, I will be covering atomic absorption and inductively coupled plasma emission. I think. Nuclear magnetic resonance is also, NMR is another part of spectroscopy, will not cover in this class. Mass spectrometry is not really interaction of light. So one thing you want to remember, you get a spectra. So here you get a spectra based on interaction with light. Here you get spectra based on ions interaction, based on detections of ion. So it's not a spectroscopy, so it's very wrong to say mass spectroscopy. It's mass spectrometry. So there's no light interaction. And we already got the lectures on mass spectrometry. Okay. Applications. Where do we apply spectroscopy and spectrometry? Both. For what reasons we use them in analysis? Michael?
Detection of pesticides.
Okay, Michael, you are very specific. So detection of components, detection of contaminants. So the word detection, okay.
Identification.
Detection, identification. Very good.
Quantitation.
Quantitation, absolutely. So we quantitate, we detect, we identify. What else do we do? What did you learn in MS? MS, for example, if you have read in MS, what did that gain? What information? Okay.
Purification.
What?
Purification.
Purification? With MS, not really. So what are you after when you do first MS and then you do a second MS? What happens? No? Structural elucidation. So looking at structural characterization, elucidation, determining the different components within the structure of your compound. Okay, so detection, identification, structural elucidation, and quantification. With quantification, we can be looking at composition analysis. We can be looking at quality assurance and forensics, looking at components within the sample to determine its quality. Or you can do quantification, not just necessarily for your general composition or macro molecules. You can do micromolecules. You can do a whole range of chemical characterization and composition analysis using spectroscopy. Okay, so here's a revision of your physics, a little bit of light. So the wave constitutes an electric field and a magnetic field. So the electric field and the blue is the magnetic field. So this is kind of your wave, and then in the wave, you have several characteristics that we will be referring to. You have the length, wavelength, lambda. So the wavelength is the distance between two repeated incidences. Two repeated incidences or the oscillation. So this is going up, down, So two repeated incidences are maximas, the two maximas. So the distance between two maximas is your wavelength. The amplitude is the energy within this maximum energy of your wave here in the electric field. So that's your wavelength, and that's the magnitude of the electric vector is the amplitude. Now, frequency is very important. What's the frequency? It is referred to as number of occurrences per unit time. That means how many oscillations. This is one oscillation, two oscillations, three per unit time, per second, per minute, whatever is the unit time. So the frequency determines the energy. The higher frequency you have, the higher is the energy. Okay, why? Because if you have, again, short wavelength, if lambda max is small, within 1 minute you have more oscillations than if it's bigger, you have less oscillations in 1 minute. So the more oscillations, the higher is the frequency, the shorter is your wave. Okay, so that relates to higher energy or shorter wavelength. Okay, so the interaction here, wave-like properties. So you have interference, you have diffraction, you have refraction. So I'll start with interference. So here you have two waves, or two light waves are going in space. If they interfere, if they interfere at the same point where you have maxima here and maxima there, then you have amplification. If they interact where the maxima and the minimum, the maximum and the minimum interacting at the same time point in space, you get cancellation of the wavelength or the light wave energy. So you get either amplification depending on how they interact, or if they are opposite, you cancel. Now, why is this important? This is important later when we study IR instruments and how the physics of the IR and how the light is constructed in a sense that the interference can be either to amplify a certain signal or a light wave, or to reduce it, depending on what we're after in terms of our analysis. So this is relevant for the physics of the instruments later on. Now, diffraction is important for us because this is what we use to have a monochromator light. So when we're doing quantitative analysis, we have to analyze at one wavelength. Otherwise, Beer's law will not be followed. So we use a diffraction system, either a diffraction grating system, where the incident beam hits the grating system and gets diffracted into individual waves of a particular wavelength. Then we can select the unique wavelength we want for the analysis. That's diffraction. And then you have the refraction, which is of the principal and refractive index, where the light in air is hitting at a particular angle. Then you measure the degree of diffraction when it hits your medium, and you can relate it to concentration. So total solids, total soluble solids, total sugars are usually determined by refractive index, which is very simple and has very good linear relationship with the concentration. But mostly, the way we're going to study spectroscopy is based on the particulate properties of light by understanding the absorption of a photon of light or the emission of a photon of light, which is basically the wave light consists of discrete pockets of energy, and these discrete pockets of energy are called or referred to as photons of light. The energy carried within the photon is related to the frequency. The higher the frequency, the shorter the wavelength, the higher is the energy. And the H is a Planck's constant, it's just a constant. But here you're just showing that the energy is directly related to the frequency, which is directly related to the length or the wavelength. So what is a monochromatic light and a monochromator? We just talked about that. A monochromatic light is the electromagnetic radiation composed of waves having a single frequency and wavelength. So that's the monochromatic light, which is very important in spectroscopy when we're doing quantification. What is a monochromator? It is the device we have in a spectrophotometer in a spectrophotometer that allows us to diffract the light into singular wavelengths. So that in the unit, in the spectrophotometer unit, what will happen is you have your incident beam from the source of light. You have a mirror, just to make the compartment small. You have a mirror that projects the light into a grating system. The light gets diffracted. Then you have a slit that you can move. That slit can be moved and allows a singular wavelength to go through onto a mirror, and then a monochromatic beam where you have a sample here and be projected onto the sample. Or instead of having a diffracting grating system, you can have a prism, which can also diffract the light or break the light into multiple wavelengths. A photon flux is basically the number of photons flowing across a unit area per a unit time. You can determine that in different manner, which you call it brightness or radiant intensity. In this case, you're not counting the number of photons, you are actually relating it to the energy. So the intensity or radiant intensity is related to the energy that is subjected to an area per unit time. So why is this all important now? Is just to define all these terms, because when we talk about different units of spectroscopy, we're going to be talking about the brightness of the light of the lamp source, how you can control that in a spectrophotometer. We're going to talk about whether you're doing quantitation. We're going to talk about Green's law later on. So you want to know that in order to obey Green's law, you have to have a monochromatic light. But in order to do identification, structure elucidation, sometimes you need to do a spectra, like we did in HPLC, where we had the PDA that gave us a spectra, which is absorption over multitude of wavelengths. So these kind of terms now will help us when we talk about different types of spectroscopy. Area, unit area, and per time. So the energy that is subjected or applied to a unit area per unit time. That's the intensity of light. Okay, so we talked about that already. So we said the shorter the wavelengths, the higher the energy, the more the frequency. So frequency of oscillations per unit time, the more you have, the smaller the wavelength, the more you have oscillation, the higher is the frequency, and with the higher is the energy. Because energy equals H, the constant, times frequency. So absorption and emission is the part of spectroscopy that we will be talking about the most. And this happens in this region: infrared, visible, and ultraviolet. That's where most of our analysis, if not all of our analysis, are going to be in this region. So usually you have absorption and emission in the region of ultraviolet and visible, and then you have infrared, mostly you're going to be measuring absorption. So here is just kind of illustration of what happens when a photon of light hits an atom. An atom within a molecule can be a singular atom or can be an atom within a molecule. So what happens is then when the light hits the atom or the molecule, if that atom or molecule can absorb light, and not every molecule absorbs light, okay? We will learn about why not every molecule absorbs light in a minute. But if the molecule can absorb light, it will absorb the energy equivalent to the energy of the photon of light, basically. So, and that energy is going to be equivalent to the change in energy from ground state to excited state. So the change in energy from ground state to excited state is equivalent or equal to the energy of the photon that hit that atom within a molecule. And then the molecule absorbs the light. And what happens if it is electronic energy, what happens here is the electron in this shell jumps up to the higher shell. So, and this is the valence electron, or the electron that takes part in the bonding or interaction between two atoms. So this valence electron jumps to a higher shell. That is in the excited state. It doesn't stay there, absorbs the light, but it's not stable at this excited state. It will have to go down to ground state. Sometimes when it goes down, it can emit a photon, which is emission. That's emission. Sometimes it just dissipates heat. But when it goes to ground state, there's always dissipation of heat. There's never no dissipation of heat. But the remaining of the energy, if the atom is able to emit or the molecule is able to emit light, the energy of the emitted photon is lower than the energy of the absorbed photon. This is important. Why? Because when you do fluorescence spectroscopy, you learn that I have to set it at two wavelengths, the absorption wavelengths and the emission wavelength. So the absorption wavelength is always lower than the emission wavelength. At lower wavelength means higher energy. So you want to remember this concept. You have higher energy of the light hitting the molecule or atom, and the energy that is released as a photon is lower because some of the energy is released as heat. So the absorption wavelength will be shorter than the emission wavelength. It's always that case. Any questions? Okay, knowing just the relationship that shorter wavelength means higher energy, and if a molecule or atom are able to emit light, it's always lower energy because some of the energy is lost as heat when you go from excited state to ground state. Okay. So atoms and molecules exist in their ground state, so there is no surprise there. So when light hits the molecule, it may absorb energy. So here's the illustration. So you have ground state, a photon of light hits your molecule, it goes to the excited state. So there is a change in energy. The change in energy is related to the frequency of your light. So the internal energy that is gained by the molecule or atom is equivalent to the energy of the photon. So I keep repeating that until it becomes really clear for you and you know it very well. So this is the important piece where some molecules absorb light, others don't, and some absorb at different wavelengths. Why is that? Because the absorption of energy is not the same, it's not a continuous thing and the same increment for every molecule. The change in energy is a different increment from one molecule to another. And some molecules, if you hit them with light, they won't change in energy because they don't absorb light. So there are three types of energies. We have electronic energy, rotational energy, and vibrational energy. So energy levels not corresponding to allowed values. Every molecule, like this, will have a specific allowed energy to change, to go from a ground state to an excited state. If you don't hit it with the right energy, it won't. It doesn't mean that the higher the energy, the more the possibility that it's going to go from ground state to excited state. No, you have to have the specific energy level that will take that particular molecule from the ground state to excited state to a higher excited state. So, for example, molecule A versus molecule B. Molecule A has these levels, E0, E1, E2. Molecule B have these levels, E0, E1, E2, whatever. So this distance here, this energy here is different than this energy there. Here, this molecule requires this much energy to go from 0 to E1, whereas B requires this energy to go from 0 to 1. So, E1. So in this case, do I need longer lambda max than here or shorter lambda max than here? Let's see if you got that concept. Difference between B and A. In B's case, do I need a lambda max shorter or longer wavelength? Michael? Longer. Shri? Longer. Okay. Nigel was pointing to Shri because he had his hand up probably before Michael. Okay. So yes, longer will carry less energy. So B absorbs at longer wavelength than A. So that's the point that I'm trying to illustrate here. It's really there is allowed value for particular species, whether it's atom or molecule. So it doesn't matter that you hit it with more energy, it's going to absorb light. No, you have to hit it with the right amount of energy for it to absorb light. And that's why there's different lambda maxes for different molecules, and not just lambda max, because you don't have, the molecule doesn't have to only absorb at one wavelength. It might absorb at different wavelength, but it just differs in the level of excitement. But don't worry about that. Okay. You just need to know that you have to have specific energy for it to get excited. Okay. So electronic energy is directly related to the electron going from one level of shell, the valence electron going to the higher level. So that's why it's called electronic And this is the highest increment of energy. Electronic is the highest increment of energy that a species can absorb. Yeah, that's exactly what I just said here. All right. So, and this is basically, I'm saying here that the energy allowable layers is equivalent to energy of photons in the UV vis radiation. So in this spectrum, the energy that can be absorbed by electrons in atoms or molecules, the energy is equivalent to the energy of photons in the UV vis radiation. So when we're measuring absorption in the UV range or the visible range, we're measuring electronic energy, absorption of electronic energy, which has to do with the valence electrons. So the UV vis radiation, lambdas, they carry allowable energy levels for electrons or valence electrons to shift in to go to a higher shell. The vibration energy, which is important in IR and infrared. So vibration, this is only specific for molecule. Atom does not vibrate. So what happened here is when you have a molecule with atoms in it bonded, the bonds vibrate. So in IR, we're going to talk about stretching of the bond, bending of the bond. So stretching and bending, these are vibrational movements. So the vibration is basically only in molecules. And if you look here, the vibration levels of energy is smaller than the energy required to shift in electronic energy. They're smaller. So IR has longer wavelength than UV and visible light. So it carries smaller amount of energy. And hence the smaller increment of energy for vibrational energy levels. So smaller energy levels, but again, the increments differ from one species, one molecule to another. That's why they will absorb infrared at different infrared wavelengths. That's what I'm saying here. It's related to IR radiation. So vibrational energy is in the range of IR radiation, or the wavelengths within the IR region of the light spectrum. The last one is rotation. So in a molecule, the atoms rotate around the center, or the molecule rotates around the center of gravity. And that rotation is also happens when it's hit, the molecule is hit with certain allowable energy level, then it will go from zero state to excited state, rotational excited state. Again, there's smaller increment than vibration. So the smaller increment of energy is associated with longer wavelength, and microwave is the longer wavelength than infrared, and that's where rotational energy absorption happens. However, in good analysis, we don't care about this part of spectroscopy. So we care about electronic and rotational. But in general, if we think of an atom, the only energy that the atom can absorb and change is electronic energy, because it's not a molecule, so it doesn't have vibration of bonds. It doesn't have bonds. It's not a molecule, so the molecule that doesn't have a rotation around its center of gravity. So the energy of an atom is only equal to the energy of the electronic energy. So again, this is reminding you it's quantized. That means they have specific increments based on the different species. And that's, again, why you have different spectra for absorption at different wavelengths. So this is what it explains the increments of energy that is unique for every molecule. That's why molecules that absorb light have unique spectra, and that's why we use the PDA that gives you that spectra of absorption over different wavelengths to determine impurity. So the last bit here that I would explain again is just, I talked about it, but it's the emissions. And what is that? What is that? Do I care about that? Okay. All right. So again, not every atom or molecule is going to emit light, but when the atom or the species goes from ground state to excited state, it needs to come back down to ground state. And it does that two ways. One way is just dissipation of heat. Now you're not going to measure emission, or it might emit very, very small amount of light that cannot be measured. But some molecules or species are very good at emitting. That means you get good intensity emission, so you can get sensitivity. But in all cases, there is some dissipation of heat. So you want to keep that in mind. The photon that is absorbed, the energy is not equivalent to the emitted energy of light by that emission or by that emitting molecules. We can say emitting molecule, fluorescing molecule. Always remember that the emission of light has a longer wavelength than the absorbed light. Any question? Great, great understanding of the topic. How about that? Yeah, great. Finished early. Do you want to start atomic absorption? We have 5 minutes. No? All right, happy Friday.
Yeah.